my name is Jeff Alstadt, and today I'm going to present on .NET Core plus Redis equals awesome, highly scalable, responsive apps. I work for Coyote Logistics and I'm a development team lead. A little bit about myself. I'm a passionate developer, speaker, and technologist. I have spoken at several developer conferences in the Chicago area, including that conference, Chicago Code Camp, Software Development Community, tech meetup groups, and internally at Coyote about Redis, .NET, C#, and C++. At Coyote, I lead a software team that is actively using Redis and .NET Core to build microservice applications that are helping Coyote to transform the 3PL logistics industry. A little bit about Coyote. Coyote Logistics is a leading global third-party logistics provider that combines a diverse, centralized transportation marketplace, matching more than 10,000 shipments every day. Coyote offers a comprehensive multimodal solutions portfolio including truckload, less than truckload, and intermodal, with data intelligence and market insights to help empower our customers' business growth in a rapidly changing world. Coyote became a UPS company in 2015, adding to our expanding portfolio of global services. We're headquartered in Chicago. Coyote has more than 3,000 employees operating in 20 offices worldwide. Why .NET Core with Redis? Well, here's why you should consider .NET Core with your Redis projects. It's fast and it can compute faster than Java. It's less complex than C++, but it's very similar in style. It's open source with Language Standards Foundation, fully supported by Microsoft and other technologies. That standards organization is the .NET Foundation and has major support from many organizations. It provides great IDEs to build your software in Visual Studio, Visual Studio Code, and Visual Studio for Mac. Visual Studio Code and Visual Studio Community Edition are completely free and you can download them today and start working with them. Also, if you don't like Visual Studio, you can also build it in any type of IDE that you prefer, or you can build it in any text editor like Atom or Sublime, etc. It can run on multiple platforms: Mac OS, Windows, Linux, AWS, Google Cloud, and Azure. It runs on any type of cloud provider. It can run anywhere Linux can run anywhere that Windows can run, and you couldn't do that before with .NET Framework. Now you can do that with .NET Core. .NET Core is not .NET Framework. They're completely two separate standards. The languages between them, C# and F#, are completely similar in their syntax, but .NET Core is the standard, and is the standard that is recommended for building new applications on the .NET Core framework. Let's look at the computer language benchmarks comparing C#, .NET Core, and Java. With a regex, you can see that C# performs 2.18 seconds fast in computation time, where Java takes 10.13 seconds. Java uses more memory than C# .NET Core for regex redux, and its CPU load is higher with Java compared to .NET Core. Binary trees, a little worse for C#, but C# still performs faster than Java. Memory utilization is about the same, and overall the load is a little higher with CPU, but Java is a little lower. Overall, C# is a better choice. And you might not think Microsoft is very open source anymore, but they are. You can see that Microsoft Visual Studio Code has one of the highest contribution rates too. In the Octoverse released by GitHub, you can see that the top two leading projects, open source projects, VS Code and Azure Docs, is run by Microsoft, and that is good to hear that Microsoft is committed to open source technologies. So let's talk about what a monolithic app versus a microservice app. A monolithic app has one code base. The code base is large. There's massive deployments. There's tight coupling. There's one database. If the cache, it's usually one big cache. All devs are on deck during the deploy. Scaling is costly, especially in the cloud. The app must scale as one big app. It's hard to unit test. It's hard to integration test. It's usually following a big onion architecture. Whereas a microservice is consisted of multiple code bases, many microservices. The code bases are small, but a large number of code that's deployed across multiple microservices. It has massive deployments. Deployments usually happen every day. It's decoupled in design because the microservice is focused on one specific thing that it does. Most microservices are event-driven. Event-driven design allows for faster deploy, faster communication between each and other microservices. Usually there's multiple databases because each microservice has its own database. Usually multiple caches for the same reason, has its own caches. Software rollout can be done. More devs can sleep at night on release night. Scaling is cheaper because it's in containers. And microservices live really well in containers. They're actually designed for containers. They're also designed for the cloud. They're cloud ready by design. They follow event-driven design, and scaling can be done in components based on the demands of the business, which means the business can scale the components that are needed to meet business needs and descale the components that are not needed currently for business needs. So let's talk about how you would move a monolithic to a microservice. Well, start thinking of breaking that service into logical components. How's it going to work? How's every little piece that currently talks to one another going to be broken down into components? You'll need to start thinking about how you can break your existing monolithic service into smaller components, smaller logical components, and how those interactions between those components can be done. Less functionality is usually better in microservice design. That's actually a core principle. You should have less functionality, and the functionality should be solely for that purpose of that microservice. It will not be done in a 2-sprint project. Expect a year to many years. For Coyote, it took us many years, and we're actually still working through our our monolithic app decoupling into microservices. It also requires a buy-in and investment and support from the business. If your business is not going to support it, it's going to fail. If business does support it, it will succeed. If done wrong, it can even be costlier than a monolithic app. That's why it's important that you do it right. Overall gains will be gained with more shipped software. Your stakeholders and your users will be able to see more and get more from using microservice architecture. It also requires an investment in monitoring. Monitoring is important because there will be many services deployed, and you can't look at the log of one service anymore. You have to look at the logs of many services, and that's not really humanly possible. What is possible, an app monitoring tool like Microsoft Insights or New Relic can give you that information and provide alerts to you if something is going wrong with your microservice in production. Investment in a message queue technology will be very beneficial and is actually recommended. At Coyote, we use RabbitMQ, and we're looking at Azure Service Bus. But some message queue technologies that exist are RabbitMQ, Azure Service Bus, ActiveMQ, and many more. You also need to focus on event-driven design or domain-driven design. Domain-driven design is a principle and it's a philosophy the organization will need to adopt and follow. You're also going to need to break up your data store into multiple data stores. I highly recommend you do that. Talking to the one database is just as bad as having a monolithic app talk to a monolithic database. And we really want to break down that monolithic database into many smaller databases that are specific to a microservice. This will actually also increase your reliability of your service because it's not one point of failure. What should be a good microservice be? Well, it should be componentized. It should be scalable. It should be designed to be scalable. It should be specific to one domain, one response, a scope of functionality. There should be high cohesion, loose coupling. It should have a stamp of identification, a purpose. It should have a RESTful API to allow for integration of other microservices to talk to it. There should be a separation of a data store. There should be usually one data store per microservice. You should have an automated deploy process. Your deploy process with using Azure DevOps and Octopus can help you deploy your services easily without hassle in getting them into production. You should focus on a schema separation. That schema is really specific just to that microservice and the tables that are involved with what that service does. You also need support for constant monitoring. You're going to need an investment into an app monitoring tool such as Microsoft Insights and New Relic. It's important that you do constant monitoring to ensure that your services are running properly in production. They can also help you identify where there's bottlenecks in your services as well. So what are some of the disadvantages of microservice architecture? Well, development is presented with more repositories since service lives in its own repository. Deployment is more complex. It's then thus presenting challenges for DevOps. Network usage will increase as apps will be more chatty with one another. There will be more complexity with security because the security is more complex since each of these microservices will have their own authentication and users. Thus, you'll need to invest in authentication and authorization to keep your data secure. Testing is a little more complex and more involved. You're going to need to write unit tests and integration tests to cover these scenarios, and you're probably going to have to write integration tests that test the microservices' interaction with one another as well. The initial investment will be high, and I guarantee you it will be high. It will be high from all parties' ends that are involved in the endeavor of building out a microservice business. Thus, it's important that you understand that there's going to be building out costs with server clusters, load balancers, API gateways, and of course the overall development cost. You should also expect a lengthier development time as well to build out these microservices. So why change? Let me tell you about what Coyote development was before. This is about the time when I started at Coyote, which was actually around 2014, 15-ish. When I started, it was a monolithic Windows application that was containing all the logical and data access operations. There was one service, few services that were involved in the whole entire organization that was tightly coupled to the business application. Teams who were always adding functionality had to be careful of touching legacy code. It was possible they could break the existing workflows, and in the past we have broken workflows and we needed to make fixes to actually make sure that they were corrected. Unit testing was hard and was also nearly non-existent. Fortunately, we've invested a lot of time into unit testing and integration tests in our newest software. It was a big onion. When we started breaking things out into microservices, it was a big onion. It's still an onion, but we're unraveling that onion even further. There was heavy hits on the DB. There was tons of stored procedures. Loading data took a while to get because there was usually a ton of stored procedures that would be accessed or read from. And releases were lengthy, often requiring entire development teams online at night for deploy. Luckily, we've fixed that now. Deployments have extended overnight if issues were found during the release, and those were never fun to do. So why change? So this is what Coyote development is now. We're a more agile, more flexible, more nimble organization. Our software can be deployed now really at any time of the day by using independent deployments. We still have a big legacy app, but it's still a much thinner client. This thinner client now uses services to talk through to get data that it needs, not talking directly to the database. It separates the applications. There's separate applications supporting different workflows. Those different workflows could be for carriers, customers, and internal employees. Our existing microservices can be deployed at any time of the day. I actually have deployed 1, 2, 3, or 4 services at any point in time at the same day as well. Our enterprise releases are very short. They're much shorter in time. They only require a few hours to deploy, only a few developers online at night for a deploy. And I'm really proud that we've actually been able to do that because our deploys when it started were much longer. Now we're really quick in getting stuff deployed, and the number of issues that arise are much smaller. The systems now use more modern tech. We're using Redis, we're using MongoDB, we're using Elasticsearch, Kubernetes, Docker, Rollout.io. Rollout.io is for more of a feature toggle service, so we can actually test things in production before we get out there, and we can turn features off if they're not working well. We're also using Azure, RabbitMQ, and SQL Server, of course. We have many repositories. Each microservice has its own repository. The same is true for each of the web apps. They have their own repositories as well. Each React app has its own repository as well. We have an automated build and release pipeline. We have to have that because we're always deploying stuff. This automated release pipeline allows us to do continuous integration, building of our software, and also deployment of our software into our QA and test environments. We have a micro-framework app built for web apps. We did this because originally we had a backbone app that was everything in it. Now that app has been broken down into multiple apps, and now within those multiple apps, we can actually deploy each app if needed on deploy. We have thousands of automated unit and integration tests. This allows for continuous integration, and these tests we continually add and we monitor. If things break, we fix them immediately. We follow a domain-driven design philosophy. So domain-driven design is a philosophy for putting software around business domains. Development talks to domain owners and product owners. We actually have a product team at Coyote. Domain owners aim to put business needs in business domains. Domain owners are responsible for working with the business and understanding what the needs are to prioritize what is needed for development to work on. Development is layered in architecture. We have a layered architecture approach. Domain-driven design is a common design philosophy used in microservice architecture, but it doesn't have to be applied to microservice architecture. You really could use it for any type of software development. Business objects are presented as models. Microservices help to define the interactions among our domains. Here's an example of the communication process, the ubiquitous language that is used to define the communication between domain experts and developers. Domain experts usually talk to designers. Designers are like your UX guys, your UI guys, and they help to identify the flow of how the application should work. The designers work with developers to communicate these design flows with developers. Domain experts also use a model language, a ubiquitous language, to allow developers to understand what they need to build and how it should be built. And vice versa, developers give feedback to designers about what they can do and what they can't do and what they recommend, and designers can work with domain experts to define those realizations to make them more reasonable. So let's talk the aspects of a layered architecture. First, a layered architecture has a user interface, an application, a domain, and an infrastructure. Let's look at a layered architecture in a microservice application. In a microservice application, the user interface would be like a web interface or a thin client. Your application would be actually the business logic or the engines, the web API that is used to actually perform the operations that are needed for the application to do. Your domain would be your models. They would be the business objects that would be used in your application. Your infrastructure is your provider, your cloud, your cache, your storage. It could also be your on-prem data center as well. Now let's talk about the app we're building today. So we're actually going to be building a simple blog app to demonstrate an app that can be deployed as a microservice. Its concepts of a good project structure, it aims to provide that, to support separation of concerns. This app is solely for making blogs. There is also a DB project that as well to support the SQL schema. In order to do that, we're using DBUp. So there's a DB project that uses DBUp. This allows to support change among the developers that are developing on the application. We're also going to provide code examples of Redis usage for specifically with caching and RediSearch. It's going to be built using .NET Core 3.1. The technology used will be ASP.NET, MVC, Redis, SQL Server, and RediSearch. We'll actually be putting Redis and RediSearch in a Docker container. Now, it's important that we talk about an important caching pattern that is very useful for enterprise applications, and that's the cache-aside pattern. As enterprise applications grow, we often find the applications will make heavy use of a data store, and most often the app needs to be read from a database and then updated. In order to mitigate the latency and excessive reads, a cache can be utilized to improve the latency, and hence desired use of a cache-aside pattern is needed. Thus, it provides many benefits. For example, it improves application performance. It also helps maintain consistency between the cache and the underlying data store. However, there is not a benefit in the fact that you do have to maintain data that is stale, and you have to maintain getting rid of stale data. So if you have no way to get rid of stale data, then cache-aside pattern probably will not work for you. But let's take a look at the cache-aside pattern with this diagram. This kind of shows how this cache-aside pattern works. Basically, an application tries to read from a cache. It checks the cache. Hey, is this customer data in here? No, it's not. So I'm going to read from the data store, which could be Mongo or SQL Server, and then on my way back, I'm going to put it in the cache, and then I'm going to go back to the application. When that same application data is read for that specific customer, it's going to read from the cache, and the cache is going to realize, oh, it's in the data store. It's in the cache. Okay, and then it's going to return that information back to the application. Now let's say the application has to do some update. Let's say the customer's address changes or something of that sort. Okay, the address changes, so that's going to be pushed to the database store. And inside that, it's going to then invalidate that item in the cache. Let's talk a little bit about DBUp. DBUp is a great package. It's a great open source project. It's a .NET library that's completely open source that supports deployment of SQL databases. It tracks the SQL scripts that have been run. It also tracks the SQL script changes that are needed to get the database current. You would write alter scripts to actually help change the database that is currently deployed. It generates a console application that can be run to create the DB tables, store procedures, and functions and views that are needed to support the application. At Coyote, we have been using DBUp for our independent deploy of microservices. And there's plenty of documentation that explains how to get DBUp set up and working in your application. Here's an example of the Redis blog DBUp being run. Here, it connects to the database, it goes to the local database, which is the local host. It begins the database update, and then it checks its journal, which is the schema versions. It checks the schema versions, then fetches a list of already executed scripts, and then it checks if it needs to execute the script, and if it does, then it will execute the script. In this case, it had to execute a script to build the Redis block table, and then it checks if there's any other tables that need to be updated, along with store procedures as well, and anything else that you would have in your deploy script. Next, let's talk about the C# Redis clients that are available. Redis actually has many clients that can work with many different programming languages, but for .NET Core, we're using C#. So the most commonly used Redis client is the Stack Exchange.Redis, and that's the one we will be using in this application. It is the one that I also recommend, is also the one that is supported by Microsoft and endorsed by Microsoft for Azure Redis. In this case, this has been developed by the people over at Stack Overflow. So also, let's note some useful applications that Redis is good for. It's good for pub/sub. It's good for caching. It's good with Lua scripting. It's good for automatic failover. It's good for LRU eviction of keys. It's good for transactions. Full page caching. You can actually use ASP.NET session storage with Redis. There's queues support for queues. It's good for leaderboards and counting, for graphs, and document search. In this case, we'll actually be using RediSearch in our application today for doing blog entry searching. Let's talk a little bit about the cloud support that exists for Redis. Redis has support on Amazon. Amazon calls it Elastic Cache. There's also Redis Enterprise Cloud. This is the one that's officially supported by Redis Labs. There's Google Cloud, which you can use. And then Microsoft has Azure, Redis for Azure. And IBM has Compose. Redis CLI is the preferred method for using Redis, but I'm a GUI kind of guy, and I like Redis Desktop Manager. I think it's very useful. And this is one of my favorite Redis desktop clients. In the picture below, in the slide, you can see Redis Desktop Manager being used. We're going to actually be using object caching with Redis in our application today. So we're going to be caching some C# models, a blog and a blog entry in Redis. And we're going to be doing this by serializing the object model to a string and then setting it in Redis and getting it from Redis. This is done using the Redis set and get commands. The Redis blog app shows examples of using a custom cache manager to support this. We're doing this by using generics, so we can put any type of C# object in there so that it can support all the model objects that are in your code base. And you can see in the code here we have an add, we have a get async and add async, we have a key exists, there's also a clear, and there's a remove. Let's talk a little bit about how Coyote is using Azure Redis. Very proud of us using Redis. It's been very beneficial to us. But at Coyote, we're using the Azure Redis. We created a common NuGet package that could be used among our many microservices. This has enabled dev teams to focus on business needs instead of cache implementations. We currently have several services using Azure Redis, and we're also using Azure Redis as a backplane for our apps that are using SignalR in production. But there's a little problem. We do have an on-prem data center where most of our production applications are stored and housed and run. So using Azure Redis introduced the problem of latency. So latency is a big problem for on-prem data center apps and cloud Azure instances. So to mitigate this, we looked at some different things and tried to figure out what we could do. We found this open source cache manager from cachemanager.mikawa.net. We've added customizations to it and then developed a Redis cache NuGet package that could be utilized by other development teams. We did a lot of testing on this NuGet package to ensure its stability and overall scalability. Utilizing a Redis pub sub that is built into the caching framework, we were able to keep both a local cache on the service that was using the cache and a central Redis cloud cache. That central Redis cloud cache, with its Redis pub sub, a local cache would check if the data existed in its local cache, and if it didn't, it would add it to a cache, push it to the central Redis cloud cache, and then from the central Redis cloud cache, there would be a push notification, push to the subscriber of the other node's caches to be updated. From this, we were able to achieve local caching among many nodes in a clustered environment. By doing this, we found in testing that the first read had some latency, but the second and third and other reads had near zero latency because these reads were all running from the local service's cache. By doing this, we've achieved a massive reduction of read hits against our SQL Server. Let's talk a little about search with RediSearch. RediSearch is a full text and secondary index engine that runs on Redis. It is loaded into Redis. It's not part of the original Redis current Redis framework. You actually have to load it into Redis. It's done via module import. It's the same thing that you would do for Redis Graph as well. It has Docker containers that exist to help expedite development that contain the RediSearch built into Redis. And we're going to be using the Stack Exchange.Redis, as I said earlier. Stack Exchange Redis has actually support for RediSearch, and that's done by Mark Gravel's work with his nRediSearch library that he had developed, and that actually has been brought into Stack Exchange Redis, and it's supported by Stack Overflow. And I wanted to thank Mark Gravel and the folks over at Stack Overflow for their development on this package. It's very helpful for us. If you're familiar with Elasticsearch, the concepts are very similar. There's a document and an index. This concept is the same as well for RediSearch. RediSearch is insanely fast compared to Elasticsearch. The reason it's fast is because it's run entirely in memory, whereas Elasticsearch actually runs on the hard drive and runs among different nodes, which means aggregations need to be done to get that data into a search result. RediSearch can be run on Windows using Docker. It does not run natively on Windows. You'll either need to use the Windows Linux subsystem, Ubuntu, or you can run a Linux Docker container if you're developing this locally. And on Linux and Mac OS, it can run in Docker, and it can also run natively because it's a POSIX operating system. To run this in Docker, you can say docker run -p, which is the port. 6383 is the outside Docker port, and 6379 is the Redis port, and then is the internal Docker port. And Redis Labs /RedisSearch latest will pull the latest Redis version and RediSearch that is currently in the Docker ecosystem. So let's talk about the RediSearch commands. The RediSearch commands that exist are ft.create, which is a command to create an index. ft.add is another command to add a document to the index. ft.search is a command to search an index with a textual query that can return document or IDs. ft.explain is a command that provides the execution plan for a query. And ft.drop deletes the keys in the documents associated with the index. If you specify the subparameter or option keep docs, it will keep the documents in place while deleting the index. Also, if you want to learn more about RediSearch, Redis Labs actually has a YouTube channel where you can watch all these videos on RediSearch and learn a lot more in detail. That's actually for another talk, but that's something to look forward to if you're really interested in Redis search. So let's get to the demo. Let's take a look at the blog app that we're going to be demoing today. So let me jump to Visual Studio and show you what I built. So here we have Microsoft Visual Studio, and we have Redis blog. Let's talk a little bit about the project structure. Currently, I have a solution called Redis blog. Then there's a project called redisblog.dbdeploy. Then I have my domain, which contains all our blog objects, or blog and blog entry. Then we have a Redis blog, which has engines. Inside these engines, they do specific blog logic. And I actually have interfaces defined to be able to support that. And then I have a storage, which allows me to store the data either in a cache or in a repository. And the RediSearch implementation is actually built into here as well. And that's, you can see in the blog entry search repository. And each of the blog entry repositories has a SQL invocation that can be used. And by doing this, we're actually using Dapper to connect to the database store and standard SQL connection to do this. And then we have store procedures that actually insert the data. And these store procedures are actually in the DB deploy project and the store procedures. So this is a blog entry insert. This will actually insert a blog entry or update a blog entry because it's an upsert. Lastly, we can talk about the web app. And inside the web app, we have our controllers. We have a blog controller, which creates a blog, and it's a standard MVC .NET Core app. It uses models and views. And we have our models, blog entries view model, and we have our views, which are our blog, creates our CRUD operations, details, edit, search, and so forth. And we have the controllers as well with the blog controller and the blog entry controller. So let's give this a run and see how this runs. So first thing I want to show is actually the DB deploy project being run. So let's run that first. You can see that it's going to build a console application. The console application is going to connect to the database and then run the update scripts that are needed. There unfortunately should not be any update scripts that are needed because the database is currently current. But let's see it run right now. Okay, and here you see the application had connected. It did its database upgrade. It was checking the database journal. There was nothing to fetch because all the scripts were executed already. No scripts to execute, thus completing it had a successful operation. And we can close that out and free up the process. Now let's run our Redis blog app. Let's run the Redis blog web app. So let me start this up. Start. It says startup project. And this will run in a local host. Let's let it start up. It's doing some things. It's connecting to IIS. We now should have our blog app started. And here you can see our basic blog app. This is just a basic MVC application. So if we click blog, it will take us to our blog. And now we have our blog. And inside here, you can see there's a few blogs that have been created. To create a new blog, we simply click create new, enter the blog, Redis blog demo, a blog for talking about Redis. Owner can just be any owner, say 5. Create. Now I have my owner, my Redis blog demo, a blog for talking about Redis. If I go to the details, I can see the actual details of the blog. I can see the owner ID, and I can see the date that's created. This date and time is actually in UTC. Now, if we go to details, we can also view the entries of the blog. Unfortunately, we don't have any entries because we just created it. So let's add some data to the blog. Start off with, this is a test blog entry. Entry, test blog entry. Create. We now created one blog entry. Let's create another blog entry. Redis is fun to develop with. Let's add one more. Let's say Redis blog rocks. This is a rocking blog. Okay, I have now created 3 entries. And from this, we can now test the search functionality and see how that works using Redis search. You'll see that with Redis, we've actually created a lot of data in Redis right now. I've opened up Redis Desktop Manager to show some of the data that has actually been created in Redis. If we refresh the key list, we'll see that there's been a lot of new entries added into Redis blog. So let me expand this and you can see here. So we created a new blog entry. So the latest blog entry that we had created, we can verify because we can see this from SQL. So if we go to SQL Server and clear this out, let me connect new query. We can see what all our blog entries are. So if we select from Redis blog blog, we can see that our latest blog entries are right here, which is 1003. This is our new blog ID. So from here, we can see that the new blog has been entered into Redis. And we can see that's in Redis Desktop, which is right here. So this blog entry, blog 1003, has been loaded into here, our Redis blog demo. We can also see the Redis blog entries that have been entered as well. So if we do select star from Redis blog.blog entries, we can see as well that we have a lot of blog entries. But our actual blog is 1003, so let's put a where clause in there, where our blog ID equals 1003. So if we F5 that, we'll get us our list here. So these are the blog entries we had entered. So now we know the blog entry IDs. We created our keys to reference the blog entry IDs. The same has been done for the blog IDs. You can now see that these items are now cached into Redis in here with our blog entries. So 1005, 1006, 1007. So all those items, so those 3 entries we had created, are all cached in Redis. We also put these items in search. You can see now that Redis has also put our blog entries in here. Unfortunately, the document IDs are GUIDs, so it's not going to be so intelligible. So we'll have to click around to find out where these are actually at. But I assure you that these were put into Redis search via the document index search. So let's take an example of how the search actually works. So let's test something that doesn't exist. So let's try entry. Well, entry exists. Let's try entry 2. Does that exist? No, that doesn't exist. Let's go back to our search results. Let's try test. Oh, we found one. There's one. Blog entry 105 has test blog entry in its title and its entry. So let's go back. Let's just try, this is a rocking blog search. Let's search is. Let's see if is returns anything. Oh, it doesn't return anything. Let's go back to the blog. We see here now, let's try, this is a rock. Let's try rocking blog. Oh, it returned something. Great. As you can see, we can now see the details of this blog entry as well. And we see here. This is the conclusion of the demo. You can now see that you can use RediSearch, SQL Server, and ASP.NET Core and .NET Core 3.1 to build applications that can interface with Redis and RediSearch. Now, I wanted to say thank you for the opportunity to present with you today, and if you have any questions, please feel free to reach out to me. My name is Jeff Alstadt. I can be reached at jeff.alstadt@coyote.com, or you can follow me on Twitter at jeffalstadt. And I appreciate the opportunity to present to you today, and I look forward to your feedback and suggestions, and wish you a wonderful Redis Conference 2020. Thank you.